Hello everyone. Today we are going to analyze this cantilever beam. In this beam there is uniformly varying load. It varies from 0 in the fixed end and to W in the free end. The span of the beam is given as L. In the fixed end A, we need to find the vertical reaction RA and the moment MA. Using the rule summation of vertical forces is equal to 0, we can find RA. RA is acting upwards, so it will be positive. The UVL is acting downwards, so it will be negative. For the UVL, we have to take the area. We know that it is a triangle. We know the area formula of a triangle, half into BH. Here the breadth is L and the height is W. So the area is half into L into W. For RA, we will get WL upon 2. Now we are going to find MA. MA will be acting in the anticlockwise direction. To find MA, I am going to take moment about A from the point B. In this case, I have to follow left hand side rule. Clockwise will be negative and anticlockwise will be positive. The UVL is acting in the clockwise direction, so it will be negative. For the UVL, we have to multiply the area with the centroid distance. We already know the area, half into L into W. We know that in this triangle, the centroid distance about this point is 2 upon 3 into breadth. Here the breadth is L, so it is 2 upon 3 into L. MA is acting in the anticlockwise direction, so it will be positive. For MA, we will get WL square upon 3. Now let us find the shear force values. I am going to find them from the point A and towards the point B. In this case, I have to follow right hand side rule, upwards positive and downwards negative. In the point A, we have a vertical reaction. So we need to find the shear force at just left of A and at just right of A. The shear force at just left of A will be 0. At just right of A, we have VA, which is acting upwards, so it will be positive. Let us find the shear force at B. VA is acting upwards, so it will be positive. The UVL is acting downwards, so it will be negative. For the UVL, we have to take the area. For the shear force at B, we will get 0. Now we are going to find the shear force at a section which is at a distance of x from the point A. We need to find this height. For the distance of L, the height is W. So for L, it is W. But I need the height at the distance of x. So we have to multiply with the x. In this way, we are getting the height as W upon L into x. Let us find the shear force at X. The reaction at A is acting upwards, so it will be positive. The UVL is acting downwards, so it will be negative. For the UVL, we have to take this area. We know the area formula of a triangle, half into BH. Here the breadth is X and the height is W upon L into X. So this is the area. So for the shear force at X, we will get this. Here you can see the shear force diagram. Now we are going to find the bending moment values. I am going to find them from the point A and towards the point B. In this case, I have to follow right hand side rule. Clockwise will be positive and anticlockwise will be negative. The bending moment at just left of A will be 0. Let us find the bending moment at just right of A. At just right of A, we have MA, which is acting in the anticlockwise direction, so it will be negative. Let us find the bending moment at B. MA is acting in the anticlockwise direction, so it will be negative. RA is acting in the clockwise direction, so it will be positive, and the distance is L. The UVL is acting in the anticlockwise direction, so it will be negative. For the UVL, we have to multiply the area with the centroid distance. We know the area. The centroid distance about the point B is 1 upon 3 into breadth. Here B is L. So 1 upon 3 into L. For the bending moment at B, we will get 0. Let us find the bending moment in the section, that is at the distance of x. MA is acting in the anti-clockwise direction, so it will be negative. RA is acting in the clockwise direction, so it will be positive, and the distance is x. The UVL is acting in the anti-clockwise direction, so it will be negative. For the UVL, we have to multiply the area of this triangle with the centroid distance. This is the area and this is the centroid distance. Finally, for the bending moment at x, we will get this. This is the bending moment diagram. Now we are going to find the slope and deflection using the Macaulay's method. In the Macaulay's method, we have to make a section. I have made a section at a distance of x from the point A. In this section, we need to find the moment. Just before we have found that, we need to equate the moment to ei d square y upon dx square. On both of the sides, we have to integrate. When we integrate this, we will get dy upon dx. In this term, there is no x, so we have to multiply with the x. When we integrate x, it will be x square upon 2. When we integrate x cube, it will be x power 4 upon 4. C1 is the constant. 2 into 2, 4. 6 into 4, it will be 24. Again, we have to integrate on both of the sides. When we integrate this, we will get y. When we integrate x, it will be x square upon 2. When we integrate x square, it will be x cube upon 3. And when we integrate x power 4, it will be x power 5 upon 5. In this term, there is no x, so we have to multiply with the x. C2 is the new constant. 3 into 2, 6. 4 into 3, 12. 24 into 5, that will be 120. We know that in the beam, in the point A, there is a fixed support. In the fixed support, there will be no slope and deflection. So when x is equal to 0, the slope dy upon dx will be 0. And when x is 0, the deflection y will be 0. In this one, let us apply both of these. In this way, we will get C1 as a 0. And in this one, we can apply x, y and C1. In this way, we will get C2 as a 0. In this equation, let us apply the value of C1 so that we will get this. And in this one, let us apply the values of C1 and C2 so that we will get this. First, let us take the slope equation. Here we can take LCM. We can keep 24L as LCM. After simplifying, we will get this equation. Using this equation, we can find the slope at any point of the beam. In the point B, x will be L. So in this one, instead of x, we can apply L. In this way, we will get the slope at B. Now let us take the deflection equation. We can take LCM. Let us keep 120L as LCM. After simplifying, we will get this. This is the equation for the deflection. In the point B, x will be L. So instead of x, we can apply L. In this way, we can get the deflection in the point B. This is the elastic curve. Since in the point A, there is a fixed support, the deflection and slope at A will be 0. We have found the deflection at B, and also we have found the slope at B. Here you can see the summary of what we have done. Now we are going to end this session. Thank you for watching this video.